So Chapter 3 is about linear programming. You are still going to use your calculator in this chapter, but you're going to use it to do the graphs. Whether you choose to do the shading with the calculator is entirely up to you. Most people find it easier to do the shading by hand than to have the calculator do it for you. I will show you how to have the calculator do it, but you have to do the same work by hand you'd have to do anyway just to get the calculator to verify that what you thought was right. So it's probably better to be sure that you know how to do it by hand. So the first method we're going to look at is the graphical method. We're going to graph linear inequalities. The difference between linear programming in the sense that it's a system of linear equations that we solve by matrices is that in linear programming we're not talking about equations, we're talking about inequalities. And in an application situation what we have is we have a set of inequalities where we're limited by, for example, maybe the amount of labor and the amount of materials to manufacture something. And yet we have a profit or a revenue function that we want to maximize. We want to be able to get the most profit out of what we've got. Or we might be trying to have a cost function and we're trying to minimize our costs. So a lot of realistic problems involve inequalities. And an example is that a factory can manufacture no more than 12 items of something on a particular shift, or a medical researcher must interview at least 100 patients to be sure that a new treatment for a disease is better than the old one. So we have linear inequalities of the form A times X plus B times Y equal to or less than C. Or you can replace the equal to or less than with equal to or greater than or less than or greater than instead of the equal to or less than. Those are used in a process called linear programming to optimize, which means to find either the maximum or the minimum value of a quantity for a given situation. Now, the linear inequalities do not have to be in two variables. You can do a system of three linear inequalities with three variables. In fact, there are instances, if you really pursue this in input-output models, where you'll have as many as five inequalities and 5 variables. We're not going to go that far because you can't solve more than a system of 2 linear equalities with 2 variables. You cannot solve those with graphical methods. You have to use something called the simplex method, and we don't really have sufficient time for you to be able to learn the simplex method and be able to apply it effectively and not shortchange other topics. So we're going to leave out the simplex method. We're not going to do simplex. So we won't have any systems where there's more than 2 variables. We're only going to deal with 2. And we're going to solve them graphically, but we'll use matrices to find the intersection points or the graph to find the intersection points. It'll be up to you which way you want to do it. So let's start with our first problem situation as soon as we define. This is what we just said, that a linear inequality has 2 variables and it always looks like one of those situations. And the numbers A, B, and C are any real number, positive or negative, doesn't matter. Negative numbers will have their potential applications, but A and B can't both be 0. A could be 0 or B could be 0, but not both of them, because then you would have 2 variables that make no difference to the outcome, and that's not a realistic situation. So here's our first example, and we're going to start out just by graphing inequalities, a single inequality. We want to graph the linear inequality 2x minus 3y is equal to or less than 12. And what we'll do is we'll begin by plotting the x-intercept and the y-intercept of the linear equation, ignoring the fact that it's an inequality. And the solutions to the linear equation in this case will also solve the inequality because the inequality has an equal to or less than sign in it. So basically, we just want to graph the line 2x minus 3y is equal to 12. So the way that we're going to do that, and I'm going to switch over now and actually graph it with you because I don't want to leave you behind.
Are you playing this on integrity?
Yes. Yes. So you will have the option of filling in your notes. Since we're going to graph the linear inequality, we're first going to look at the equation that's related to it, which is 2x minus 3y is equal to 12, and we're going to find the x and y intercepts. If we find the x-intercept, we're going to let y be 0. And that gives us the point 60. We choose to find the intercepts because they're the easiest 2 points to find. And then we're going to do the same with the y-intercept, except we're going to let x be 0. And y is -4. So we have 2 points, 6, 0, and 0, -4. So we're going to graph that equation first of all. So there's my x-axis. There's my y-axis. And you'll find that I don't always center my x and y-axis because you don't necessarily always have to. And in a realistic situation, we're really only going to be using the first quadrant in a lot of these problems. But we can plot the points here, 6, 0, 1, 2, 3, 4, 5, 6. So there's 6, 0. And 0, -4. 1, 2, 3, 4. And then because this inequality is equal to or less than, then any line that I draw will contain solutions to the inequality. So the line is actually going to be part of the solution. So that's the name of the line. And now comes the part where you have to decide what the rest of the solution is. So for the rest of the solution, I need to determine whether the solutions are this part of the graph or they're this part of the graph. So looking at equal to or less than, I need to pick a test value, a test point x, y, and plug into that inequality and see if that test point works. Now the easiest test point to choose, if it's not on the line, is 0, 0. Because substituting in 0 leads to fewer arithmetic mistakes. So our test point is going to be 0, 0. So we say, is 2 times 0 minus 3 times 0 equal to or less than 12? Well, 2 times 0 is 0, 3 times 0 is 0, and 0 minus 0 is 0. Is 0 equal to or less than 12? Yes. That is a solution. Therefore, because that one is a solution, everything on this side of that line, every single point, is a solution. And if you want to verify that, then you can pick any other point that you want to. And I'm going to be lazy. I'm going to pick the point 1, 1. right here.
Okay, so from the point that you tested, if that point does not work.
Then
and
you
it's
go the
not on
other way.
And it's
We
not-
would have shaded this way,
Okay.
okay?
But
So
if
it's
it
a,
doesn't-
it's a yes or no question. If your test point worked, go from the line toward that point. If the test point did not work and your answer is no, then don't go toward that point, go to the other side of the line. But I can verify this is correctly shaded because if I plug in 1, 1, then I have 2 times 1 minus 3 times 1 is equal to or less than 12. And that is 2 minus 3, which is negative 1, equal to or less than 12. And yes, of course it is. So I just verified that this is the correct direction to shade. You don't have to verify that. I could pick any point over here that I wanted to, and all of them should work. But if I were to pick, for example, 6, negative 1, right there. And we try 6, negative 1, we're saying 2 times 6 minus 3 times negative 1 is equal to or less than 12. Well, 2 times 6 is 12. Negative 3 times negative 1 is positive 3, which is 15, and 15 is not less than 12. So that one didn't work, and no point on this side of the line will work. So this is our solution. This green area, all of that green area that's on that side of the line, or everything basically above the line, is the solution. Okay? So that means in order to actually write the solution to these problems that we're going to be doing, you're going to have to actually draw the graph and shade it, because the shading is the solution. Okay? Is everybody good so far? Any questions? Making sense? Okay. Let's try another one. X minus 4y is greater than 4. Again, we're going to start by graphing x minus 4y equals 4. So we're going to find the x-intercept. X minus 4 times 0 equals 4. X equals 4. So we have the point 4, 0. And then the y-intercept, we're going to let x be 0. 0 minus 4y equals 4. Y equals 4 over negative 4, which is negative 1. So we will plot those 2 points. Zero, negative 1, and 4, 0. And this time we're not going to shade in the line with a solid line, because this doesn't include equality. So when you have either greater than or less than without an equal sign, then when you graph your line, you're going to graph it with dashes, because the line actually is not part of the solution. It's just a boundary. I'm sorry, that's supposed to say equals because that's just our boundary line. Okay? Then we're gonna do the same thing we did before. We're gonna choose a test point. And again, since 0, 0 isn't on the line, it's okay to pick 0, 0 because it's easy. So we're gonna test by saying, is 0 minus 4 times 0 greater than 4? 0 minus 0 is 0. Is 0 greater than 4? And the answer is no. Agreed? So that's not part of the solution. And since that's not part of the solution, then we're going to shade away from there. We're going to go to the other side or below the line. So here's our solution. And notice it does not include the boundary line. It goes all the way up to it, but doesn't include it. So that's the solution to x minus 4y is less than 4. Only points that are below the line. Question?
Because there's no equal sign under
There's no equal. On the first problem that we did, we had equal to or less than.
Oh, okay.
Okay? And even if we had equal to or greater than, the fact that we have an equal,
The greater than, the equal.
yeah, it's the equal that makes it solid. If you don't have the equal, if you just have less than or greater than, then you make it dashed. Okay? Making sense so far?
Why'd you flip the sign?
I
Your
didn't.
solution?
And oh, sorry. I shouldn't have. Always ask. I'm glad you'll ask.
Well,
Yeah.
yeah, because I was like, I was like.
Now, why did you do that? Yeah, I shouldn't have. I just copied it wrong.
Okay.
But again, the solution is the shaded area. There's not a way to write it as ordered pairs or anything like that, or other than x is less than or y is less than thing. You've got to actually shade the area on the graph. So you're going to do some graphing this time. Okay? Now, this one is your turn. Graph 3x plus 2y is equal to or less than 18. is about done. Give you another minute. Okay, so your boundary line is included, which you 0, 0 for your test point. Find that 0 is equal to or less than 18 is true. So the correct half plane is the one that contains 0, 0. And your graph should look something like that. Okay? And there's the one that I came up with. So if you got that one, I think you understand this.
Wait a second. Do you have to write it, okay, on the first one, when you wrote the solution in the problem, I think you wrote 2x minus 3y equals 12, or did she do? Okay, so that was just not.
Now, I just label the line. You can label the boundary line, but be sure you use an equals when you do it.
Okay. So you wrote that one there as the solution?
I'm writing that the solution is the shading.
Okay, so I don't have to write.
So you don't have to actually write the inequality there because the solution itself is the shading.
Okay.
Okay? Now, this is the calculator part. You could have used the graphing calculator to help you with graphing that inequality. But in order to do that, you would have had to have first solved your equation for your boundary line for y, which means you would have had to subtracted 3x from both sides and then divided everything in the equation by 2. So the slope-intercept form of the line is y equals negative 3 over 2x plus 9. So you would have to enter that into your calculator and graph it and get this answer. Now there's a couple of different graphing calculator shortcuts that would have let you test the point 0, 0, but they require a lot of extra button pushing, and honestly testing 0, 0 in your head is not that hard. Because if you go back and look at your original equation, if this is 0 and this is 0, then that whole side of the equation is going to be 0. So it's not hard to ask yourself, is 0 equal to or less than 18? And the answer, of course, is yes. So we know that given this graph, we're going to shade in this direction. Now, if you want to use the calculator to help you, take into account that this is below the line. This is going from the line down, okay? So what we do, and I'm going to demonstrate this for you, is this is the end result of getting the calculator graph, and it will graph and shade for you. But this is what you've got to do to get the calculator to do that. You have to first solve the equation as I showed you. If you don't have the TI-84 that puts your fractions in as number over number, you need to put your fraction in parentheses. If you have the 84 that makes it look like a fraction, you don't have to. And I'm just going to zoom 6 for standard window.
Hold on one second. You did 18 instead of the 9?
Oh, I'm sorry. Yes, that's supposed to be 9. Thank you. I shouldn't talk and enter at the same time. Okay, so there's your graph. Now we look at 0, 0 and say, okay, is 0 less than 18? Yes. Did I go too fast for you?
Yeah, I don't know what you hit after you hit, after you had it in the y equals, what did you hit?
Okay, I went to zoom, and since I figured that it's gonna be on, you know, really close to the origin, that I just chose number 6, which is the standard window, goes from -10 to 10, both directions. And if that hadn't showed me the graph, then I would have started hunting, but since that one did, then I'm happy with that one. And I know now that I need to shade below the line, so this is the last step. Here's what you actually have to do to get that little symbol there. You move your arrow to the left, and this is actually on your handout. You move your arrow to the left until you're sitting in front of Y1. And notice that the line in front of Y1 starts flashing. If you hit enter repeatedly, it'll change through several different things. The first one is just a heavier line. And that would be useful if you're looking at 2 lines and trying to decide which one is which. But that's no interest to us here. So then the next thing it does is it shows flashing above the line, which means you would want to shade above the line, and that's not what we want. So we hit enter again, and it goes to the part where you shade below the line. At that point, if you hit enter, it keeps on going through the different things. So you want to pick the one that has it flashing below the line and then move away from sitting on that symbol. Just press your right arrow and get off of it. Okay? And hit graph. And it will indeed shade. But I don't know if it's worth going through all of that.
No, because, I mean, if we're already choosing which side.
Yeah, if you already have to
Why do you
choose the
need
test
that?
point, why do you need to get the calculator to show you? Now, it might be useful to be able to check out your X and Y intercepts, I don't know, but I'm gonna show you that you can graph on the calculator.
You pick what side.
Yeah, you pick what side anyway, you still have to test your point.
Yeah.
So, you know, if you wanna do this, you can, but you don't have to.
Well, I guess it looks pretty.
Yeah, it looks pretty. I don't want to deprive you of being able to use the calculator if you want to. However, on this particular set of work, I don't think it's useful like it was back in doing matrices.
Understood.
Okay, so here's the summary of the steps. Draw the graph of the boundary line, make sure the line is solid if the inequality involves equal to or less than or equal to or greater than. Make the line dashed if the inequality is either less than or greater than. Then you decide which half plane to shade, because it divides it basically, your line divides your graph in half. So you decide which half to shade by choosing a test point. Now, this one says solve it for y and shade above if the inequality is of the form greater than or equal to or greater than, and below if it's equal to or less than. I don't recommend part A, because we're not going to go through about, okay, when do I flip the sign over when I divide on both sides? That's too much stuff to memorize. It's much easier to use the test point. So I recommend part B. So choose step 2B. Choose any point not on the line as a test point. Shade the half plane that includes the test point if it satisfies the original inequality, and otherwise shade the other side of the boundary line. So it's pretty cut and dried. Now the next thing we're going to do is graph a system, meaning more than one linear inequality. And it works pretty much the same way. First thing we're going to do is we're going to graph the boundary of the first system, which would be y equals -3x plus 12. And because the symbol is going to be less than, then we're going to use a dashed line. And we're going to shade below the line because 0 is less than 12. Because if this is 0 and that's 0 is less than 12. So 0 is less than 12 is true, so we're going to shade toward the origin. Okay? Then we're going to graph the line x equals, x is less than 2y, but we're gonna have to change it around and solve it for y. So x, it turns out that y is greater than 1/2 x, or y equals 1/2 x. And we're gonna again test the point 0, 0, which is gonna come out with 0 is less than 0. We're gonna have a little bit of a problem, because 0 is not less than 0, but it's not greater than 0 either. So that means we can't test 0, 0, because 0, 0 is actually on the boundary. So we're going to see what we do when that happens. So ultimately, this is where we're going to wind up. But I'm going to walk you through the steps of how we're going to get to this, okay? So here's what we do first. We're going to graph y equals negative 3x plus 12. And since that's already in slope-intercept form, it's easier to graph that one by plotting its y-intercept and then using the slope to get our second point. And since I know I'm going to need to go up to about 12 on the y-axis, I'm going to put my x-axis down fairly low. So 0, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I could also have just put it in the center and counted everything as twos, but we'll leave that at 0, 12. And then we're going to count down 3. 1, 2, 3, and right 1. And that's our next point. And then we're going to draw the line. And because this says less than, our boundary line is going to be dashed. So this is the boundary line, y equals negative 3x plus 12. We're going to test the point 0, 0 because it's not on the line. And that tells us 0 is less than negative 3 times 0 plus 12, which means 0 is less than 12, and that's true. So we're going to shade this way. So there's the first one. And then we'll move on to the second one. X equals 2y. And right away you're going to notice that your favorite test point, 0, 0, is going to be on that boundary line, because 0 is equal to 2 times 0. So you're not going to be able to test 0, 0, although we do know that it's on the line now. We can pick a different value for y and figure out what x is. Let's say x is 2 times 1, let y be 1, x is going to be 2. So that's the point 2, comma 1. 1, 2, and up 1. Or you may have wanted to pick x to be a different number, or you may have wanted to be given a value to x and figure out what y is. So let's say we had chosen x to be 4 and want to find out what y is. Well, 4 equals 2y. That means y is equal to 2. So the point 4, 2 should be on that line. 1, 2, 3, 4, and up 1, 2. So here's what that line looks like. And again, we're using a dashed line because there's no equals to in that inequality. But since we can't use our favorite test point, we've got to pick another one. Anybody have a point that they would like to choose?
That's not on the line,
That's not on the line.
but
1, 1?
one on
No, it's not,
well,
because 1 doesn't equal 2. Okay, so let's choose 1, 1. That means 1 is less than 2 times 1, and 1 is less than 2. And that's true. So remember, we're talking about the purple line, not the red line. So we're going to shade toward 2, 1. Now, take into account that these are solutions to x is less than 2y, just like these are. And these are all solutions to x is less than negative 3x plus 12. But the only place this overlaps is in this area right here, where you see both purple and green. So that's actually your final solution, is this area here where this all overlaps. You wouldn't have to do any extra shading as long as you shade it to where you can see that it's overlapped. But that is the solution region right there. Okay? It's this part in this corner. The name of this region is called the feasible region, because it's the region that has all the solutions. It will be helpful in the next chapter, or the next section, although we don't have to do it here. It'll be helpful for us to know points like these in the next one, because those will be called corner points. Okay? So it'll help us, it will be helpful for us to know those intersection points. And for that reason and that reason only, it may sometimes be worth it to actually graph these on the calculator to be able to determine your intersection point if you don't want to do it algebraically. But we'll cross that bridge when we need to. And just keep in mind that the corner points are going to be important in solving these in application problems. So for a quick summary of what we just learned, we graphed negative 3x plus 12 is equal to y and made it a dashed line, tested 0, 0, and determined that we were going to shade in that direction. Then we graphed x equals 2y with a dashed line. We couldn't test 0, 0 because 0, 0 was on the line, so we tested 1, 1 and found out that it is a solution to x is less than 2y, so we shaded in that direction and found that the overlapping shading is this part right here. If you had done this on the graphing calculator, it would have looked like the part over here, only it doesn't have the colors. Although if you've got the newer TI-84 that has the color, you can actually choose different colors for your shading. So the calculator will show you the same thing. It'll show you shading in this direction. And if we had done this on the calculator, the shading for this direction here would have gone vertical rather than horizontal, so you can see the overlap. Okay? So we're going to do one more, and this one's a little bit different. We want to graph the feasible region for the system y is equal to or less than negative 2x plus 8, and x is only between negative 2 and 1. Those are the only feasible values for x for whatever reason, since this is not an application. So the way that we're going to do that is we're going to graph y equals negative 2x plus 8. We're going to go ahead and do that on paper first, before I show you the final result. So on paper, I'm first going to graph y equals negative 2x plus 8. The y-intercept is 0, 8. The slope is negative 2 over 1. So the point 0.08 is 1, 2, 3, 4, 5, 6, 7. Oh, I didn't plan very well this time. 2, 4, 6, 8. I'm going to go by 2s. And that means that when I go down 2, that's down 2. And then right 1 would give me this point right here. And then if I go down 2 more and right 1, that would give me that point. So everything does line up. And this is equal to or less than, so I can make this line solid. So this is the line y equals negative 2x plus 8. Now I could go ahead and shade. I'm not going to yet. I could go ahead and shade. But what I'm going to do before I shade is I'm going to take care of the second system, or the second part of the system, which is that x can only be restricted to being from negative 2 to positive 1. This would be x is negative 2. And that means that this where x is equal to 1. Notice they're both vertical lines. And the only values that I can use are the values that are in between those two lines. I can't use any values out here, neither one. So when I test to see which side of this to shade on, I want to stay between those two lines when I start doing my shading. And I can still test 0, 0 because it's in between there. So I'm going to test 0, 0. And 0, 0 is definitely in between, so it's a legal x value. But is it a legal value up here? So 0 is equal to or less than negative 2 times 0 plus 8. 0 is equal to or less than 8. That's true. So I do everything that's between these two lines, but below this part. So there's my solution area. Not everything on this side of the purple line, only the part that's in that band from negative 2 to 1 for x values. Now that's a little different. Does anybody have any questions on that one? And that area that I shaded in there is called the feasible region, which is the same as saying it's the solution to that system. Anybody have any questions? So I did graph it for you in the PowerPoint, but I wanted to be sure that you understood step by step why it doesn't look like what we did before. Now we've got another one that's going to be your turn. So I'm going to give you a chance to make sure that you know how to do this. you need to graph boundary lines and then shade, which you have where you're supposed to shade.
Am I going in the right direction now? I mean, I solved it.
Yeah, that works.
Okay.
So you would do your line intercept is 0, -3, and then you would go down 3 and right 4 to get your second point. And that will be your boundary line. Okay?
For that,
For the first one. And yours is right. The first one, to get it as far as you got.
Yeah, I don't know.
Yeah.
Just holding up.
You have to do two first.
Yeah. Like, well,
And you put it in.
we're all-
Still have the second line. I don't know.
Your second line, your boundary line is actually x plus y equals 0. So that means x and y have to be the same for all the points. So it'd be points like 0, 0, 1, 1, 2, 2.
Oh, just
Oh,
like
I'm sorry,
that.
wait, no. Yes. X could be 1 and then y would be -1. X could be -1, y could be 1. They have to be opposites of one another so that they'll add up to 0. Okay? Yeah, good job. Let me go ahead and show you the solution that I have. My part of it is minimal. I did not do a lot of work because you might have done things a little differently from what I did. I graphed 3x minus 4y equals 12, which is this line. And then I graphed x plus y equals 0, which is this line. And when you're graphing x plus y equals 0, keep in mind all you're saying is that x and y have to be opposites. 2 plus -2 is 0, 1 plus -1 is 0, -1 plus 1 is 0. So as long as you pick the same number and change the sign on one of them, all those points should be on that line, and that's this line. Okay? But 0, 0 is on that line too, because 0 plus 0 is equal to 0. So that means you can't use 0, 0 for your test point for that line. So what you have to do is pick something else, and like I chose -1, -1, -1. And -1 plus -1 is -2, which is not more than 0, so you have to shade that direction. And then just to prove the point that you don't have to always pick 0, 0, for the purple line, I picked 1, 1. 3 times 1 minus 4 times 1 is 3 minus 4, which is -1, and that's not equal to or greater than 12, so I would shade on this side, and my solution or my feasible region is here. Okay, now you may have gone about it a different way, but your graph still should look like that. The goal is to get your graph to be correct. Regardless of what path you take, it should still lead you to the right graph. Now, before I go on, let's see, how many more do we have left? I think we're close, yeah, we're close to the end of this section. So before I go back to the PowerPoint, I'm going to go quickly through this one and explain to you what the only thing that's different is. The only thing that's different here, you're going to graph 2x minus 5y equals 10, and you're going to use a solid line because it's equal to or less than, and you're going to graph x plus 2y equals 8, and again it's going to be a solid line. But what's different here is you're restricting x to being positive numbers, and y is also positive numbers or 0. So you don't even need to draw a grid in the middle. What you need to do is only include your first quadrant. So there's no point in even drawing the rest of them. The only quadrant where both x and y are 0 or positive is the first one. So by restricting my graph to this quadrant, I've taken care of those last two inequalities. And now I only have to worry about the other two. So let's see, for 2x minus 5y equals 10, if y is 0, x is 5. And if x is 0, y is negative 2. That didn't help me much. Slide it up.
Slow down.
Slow down, okay. So knowing my y-intercept here didn't help me much, because I didn't leave it on my graph. But I can still use the fact that this is -1, -2 to draw the line, which is all I really needed to do. So my line needs to go like this. It would continue on down here, but this part is not going to be part of my feasible region, because it's where x is below 0 and y is below 0 also. And then if I choose 0, 0 for my test point, which is my favorite point, it's true. So when I shade that part, I'm going to shade this way. Okay? And then I'm going to look at x plus 2y equals 8 and try to draw its graph. Let's see, if y is 0, x is equal to 8. And if x is 0, y is equal to 4. That would be this line. And the line does go on, but I don't care about anything except the part that's within this quadrant. So I can still test my favorite point because it's not on the line. 0 plus 2 times 0 is equal to or less than 8. And 0 is, in fact, equal to or less than 8. So I'm going to shade from that line toward 0. So it turns out that my feasible region is only this part right here. And my feasible region is called a bounded. feasible region because it has solid lines on all of its sides. So that's called a bounded feasible region. Every single solution is contained inside that little quadrilateral. Now, if my feasible region had been this region out here, which it could have been, if it had been this region out here, it would have been called an unbounded feasible region because it's bounded here, here, and here, but it wouldn't have been bounded in that direction. It would have kept on going in X and Y, getting larger and larger. So that would be called an unbounded feasible region. Okay? Now, I know I went a little quick on that one, but I want to let y'all take a short break before we try to do anything with 3.2 and 3.3. So let's take about 10 minutes, get up, walk around, wake up. We'll wrap this up with a quick review of what we've seen so far. I don't expect you to, I will leave this in the recording so you can fill in the very last example, example 6. But I went ahead and did example 6 without asking y'all to do it with me because it's more important that you see the result than it is that you actually go through it because it's the same as what you've done before, but the outcome is not the same. So we did example 5, and we found that this was a bounded feasible region because it has a solid boundary on all four of its sides. Now, there may be more than 4 sides if there's more than four equations. So, as I explained, a feasible region is bounded because it's completely enclosed by its boundaries. The feasible region in examples 3 and 4 are unbounded, and we'll go back and look at those. So here was example 3, and this feasible region is unbounded because it's bounded here and here, but on these other borders out here, it is not bounded. It continues to go on forever. And example 4, even though it's bounded even on 3 sides, it is still not bounded at the bottom. So it's also an unbounded feasible region. And that's going to be important as we get into the applications problems because sometimes an unbounded region will prevent you from optimizing depending on what you need to have, whether it's a maximum or a minimum. So the example that we're looking at now is the feasible region for the system negative 3x plus 4y is equal to or greater than 12 and x plus 3y is equal to or greater than 6. So what we do is we graph each one of the inequalities and choose the appropriate half plane. And the feasible region should be the region where all of those overlap, where all the different shading overlaps. What you're going to see is there's no feasible region for the system, and therefore no solution to the system. Now the way they show it to you is this way. Negative 3x plus 4y is equal to or less than 12 is the blue line. And our test point 0, 0 fails, so we shade in that direction. X plus 3y is equal to or greater than 6 is the red line. And it goes in this direction. And if we stopped there, we would have an unbounded feasible region where it's gray. But it doesn't stop there. It says that there is also the restriction that y has to be equal to or less than 1, which means that it has to be below that green line. Well, none of the feasible region is below the green line. So what happens, honestly, and I'll show you a different version of the picture, but it shows the same thing. Here's your solutions to negative 3x plus 4y is equal to or greater than 12, and they go above the line. But below the line, y equals 1. So there's a potential overlap. But then when you graph this one, x plus 3y equals 6, You also have to shade above that line, but you can only go up to the line y equals 1. So we've got this area, and there is no overlap. So there is no feasible region that satisfies all of the inequalities. So if you have no feasible region, don't say, oh my gosh, I've done something wrong. There may be no solution. Okay? Now we've got a manufacturing example here. And I think what I'm going to do is I'm going to walk you through the problem and let you fill in your notes kind of as we go along, because in the next section, I'm not sure we're going to have enough time to take the test. So the reason I told you, yeah, we're going to have to come on Halloween is I think y'all's test is going to be on Halloween night.
That's terrible.
You can't?
No, I mean, I have this handle with my kids and my, oh my God.
Okay, then let's do it this way. Let's go ahead and have class next week. Because I was afraid I might run into that, because I looked at all the people that were in this class and thought, oh, some of them are parents, or and if not, grandparents like me. And yet I don't think we're really gonna be ready to take the test next class period. We're gonna need some more time from tonight, and we've got an application plus 2 more sections. So let's do it this way. Let's have class next week. At the end of class, I will open the test.
Oh, so we wasn't gonna have classes next week?
No, we are gonna have class next week. We were gonna have the test next week, but I don't feel like we're gonna be ready for the test next week.
Is
That's
the
what I'm
test
saying.
over chapter 2?
It's over chapter 2 and 3.
I thought you were gonna give us the option to do it over 2, just 2, and then to do it over chapter 3 too. Am I lost here, or did she say that?
You can have the option if you want to do it that way. In that case, we'll have the test next week and then finish chapter 3.
Yeah, that's.
Let's do
Let's
that,
do
'cause I don't wanna mix
Wanna do
2 and
that?
3 together, no. Like,
Okay,
I mean, seriously.
then that's the plan. Now, that means your plan's gonna be different from my day class, because the day class didn't get that option. But they didn't miss so much on fall break as you did. Okay, so the test will be next week over chapter 2 only. We will have a separate test over chapter 3 only. I will open it on Halloween night.
Will we be done next week?
Yeah, because we're gonna be done next week. I can finish
Oh,
it.
so after the test, next week, we're gonna have class?
You're gonna have class. I normally don't do that, but what I'm gonna do is I'll give you the test on Halloween night, but it's gonna be open for 3 days. So it'll be open October 31st, November 1st, November 2nd. Anytime in that 3 days, I will give you 2 hours to do the test, and it'll be over chapter 3 only, and you'll do it out of class. Your exam 2 score is gonna be the average of the chapter 2 test and chapter 3 test. Okay? I will average those together as if they were one test. So what we're doing is we're doing a half test and another half test. Everybody understand? Okay, now the question is, do we come on Halloween night? Well, with as many parents as there are in here, if you tell my daytime class, I'll shoot all of you. Because they're gonna be mad because somebody got a day off. 'Cause
Don't give them access to this integrity lecture.
well, they don't get this integrity lecture. They don't get your integrities, and you don't get theirs unless I don't get to record in both classes. So their test is gonna be as scheduled, and they'll have to have class on Halloween, but they're not coming at night, and you guys work. So I'm gonna give you Halloween night off, but the trade-off is you're gonna have to go ahead and watch the chapter 4 lesson that I'll post before you get here the next Monday night. Okay? It'll be a Nearpod lesson. I'll make sure that you've got the notes. I'll go ahead and I'll actually probably record their lecture for you to have to go over it too. But the Nearpod really will probably get you started. Okay? So you can have Halloween night off.
Thank you so much.
I've got a grandchild too. I don't even get to have her on the 31st, but I know if I did get to have her on the 31st, I'd want to be there.
We've got parents in Bluff City and Bulls Gap, and so we go to both and we take them and it's.
I know, and it's hard. It's hard.
It's a whole.
So that's our compromise. We do have tests next time. We will finish chapter 3 next time. We're going to finish chapter 3 as much as we can tonight. But then we will take Halloween night off as long as you agree that you have a take-home test and a lesson to preview before the next class. Fair enough?
Yes.
Okay.
Thank you.
You're welcome. I understand. Been there. Am there. Okay. Manufacturing example, then we're going to go on to the next section. Happy Ice Cream Cone Company makes cake cones and sugar cones, two different kinds of cones. They both have to be processed in the mixing department to make the dough, and then in the baking department to bake the dough, to make the ice cream cones. Manufacturing one batch of cake cones requires 1 hour in mixing and 2 hours in baking. Producing one batch of sugar cones requires 2 hours in mixing and 1 hour in baking. Each department is operated at most 12 hours a day. That information gives us enough information to come up with a system of inequalities. The number of units made are our variables, X and Y. X takes 1 hour in mixing and Y takes 2 hours. So 1X plus 2Y is going to have to be equal to or less than 12 hours. For the sugar cones, they take 2 hours in mixing, but 1 hour in baking. So we're going to also have 2x plus 1y is equal to or less than 12. Okay? The table helps you organize the equations. Since the amount of time in each department can't exceed 12 hours, we'll set each department's total number of hours to be less than or equal to 12. It is not possible, and this is not listed on this table, but this is a common sense requirement. It's not possible to make a negative number of either product. So X can't be anything but 0 or positive, and Y has to be 0 or positive. So from this first row, from the second row and the third row, we get these two equations. The mixing department is 1 for the X cones and 2 for the Y cones. It has to be equal to or less than 12. Remember that X is cake and Y is sugar cones. So 2 hours for the cake cones and 1 hour for the sugar cones has to also be equal to or less than 12 in the baking department. So your two variables are the number of sugar cones and the number of cake cones. X is the cake cones, Y is the sugar cones, as it says here. This is your system of equations for that problem. We need to graph that system of equations. Now, we've slowly and painstakingly graphed every one up to this point, so I'm going to actually skip over quite a bit of this. You're going to have to go back and fill in your notes on the graphing part, because we've graphed a lot, and if you've got sufficient time, I know you can do it. So ultimately, this is what our graph looks like. Okay? This is restricted to X and Y being greater than 0. It turns out that 0, 0 works in the blue equation, and it works in the red equation, because 0 in both cases is definitely equal to or less than 12. So this is our feasible region. Don't worry about what those two green points are just yet. Okay? That's our feasible region. So on the next slide, it says, using the graph from part B, can 3 batches of cake cones and 2 batches of sugar cones be manufactured in one day? That means, is the point 3, 2 in the feasible region? Where is the point 3, 2? It's in the feasible region, so that is possible. Okay, the other question is, can they make 4 batches of cake cones and 6 batches of sugar cones in one day? And you almost shouldn't even have to answer that, because considering that one or the other of these is going to be doubled in both of the equations, you're going to exceed the potential amount for 12 hours. And the 0.46 does indeed fall completely outside the feasible region, so that's not possible. Okay? That's the end of that problem. Graphing the feasible region will tell you if certain solutions are possible or not. We haven't gone into the idea of optimizing yet. Optimizing is where can you maximize or minimize profit. So we haven't gone into something called an objective function. But we have applied systems of linear inequalities. So at this point, I'm actually going to switch over to the next set of problems, which is on a different handout. I'm sorry, not a different handout, a different PowerPoint, because I broke the PowerPoints up. We're going to talk about solving linear programming problems graphically, but we're going to add one more item to that. So we're still graphing linear inequalities and systems of them. But now we're going to have to add what's called an objective function. A lot of mathematical models designed to solve problems in business, biology, and economics involve finding an optimum value, optimum meaning a best value. It might be a maximum, it might be a minimum. In linear programming, you have to find a maximum or minimum value of something called the objective function, which, as I've said before, is sometimes a cost function, sometimes it's a revenue function, sometimes it's a profit function. Sometimes it's a supply or demand function, but not as often. And it has to satisfy the set of restrictions or constraints, which is the other linear inequalities. So as long as we only have two variables involved, the solution to a linear programming problem can be found by graphing the set of constraints and finding the feasible region, which is all of what we did the first part of class, and then to see how to use the feasible region to determine the optimum value of the objective function. So we're going to start out adding the one new thing to what we've been doing, and that is the objective function. So this is example 1. If you didn't get all your notes on that slide, it's in the recording. You'll be able to go back and fill in your words. This is it. What's on your notes is exactly what was on that slide, word for word.
I didn't see that bottom.
I just see the bottom paragraph.
It said, one is a point in the feasible region where the boundary lines of two constraints.
Corner point, I'm sorry, that comes up in a later slide, but I put it there. A corner point is a point in the feasible region where the boundary lines of two constraints cross. And I'll define that as we come into this next problem. Okay, so here we have this problem. It's not very different from the problems that we did in the last section. We've got 2x plus y is equal to or less than 4. Negative x plus 2y is equal to or less than 4. X has to be 0 or positive. Y has to be 0 or positive, which means that we're going to restrict our solution to the first quadrant. And the easiest way to do that is when we graph it, don't even graph any of the other quadrants, just graph the first one. So when we graph, this is what it's going to look like. And what we find out when we graph this is that the boundary line for 2x plus 4 plus y is equal to 4 is this steeper line with the negative slope. It has an x-intercept of 2, 0 and a y-intercept of 0, 4. This one has an x-intercept of 0, 2, I'm sorry, a y-intercept of 0, 2 and an x-intercept that is going to be negative, so it's not actually going to show up here. So what we would do here is just pick another point to find its other values. We could pick a point like let x be 2 and find out what y is. So you may not be able to always use the intercepts to graph these. If you want to do, as I saw Eddie was doing earlier, if you want to solve these for y and graph them on your calculator, that's okay too. It might make it faster, it might not. You have that option. But you're going to need to graph both of those boundary lines And then your boundary lines are your X and Y axis restricting it to the first quadrant. So as it turns out, the feasible region is this blue region in here. And the feasible region is actually bounded by the point 0, 2, which is the y-intercept of negative x plus 2y equals 4, and by 2, 0, the x-intercept of 2x plus 4y equals 4. The only point we don't have is point A. Now there's two ways to get point A. And since point A is what I'm looking for, I'm going to switch over here and I'm going to show you both the ways to get point A. You can get point A by setting 2x, let's see, we're going to need to solve these both for y. So we're going to take 2x plus y equals 4, that's the boundary line, and we're going to solve it for y. Okay? Then we're going to take this equation, negative x plus 2y equals 4, and we're going to solve it for y. So there's our two equations. Now, we can either graph, which we will do in a second, or if you're wanting to do it algebraically, the y values to these two equations are going to be the same when their rule is the same.
Isn't that supposed to be a negative?
Which one?
When you solve for the, when you solve for the y for the second part, when you got a negative x in front of it.
Negative x, if you add x to both sides,
Okay.
will become positive, okay? Now that's okay. That's okay. So we're going to set these two equal to each other. Negative 2x plus 4 is equal to 1/2 x plus 2. We're going to add, well, let's not deal with fractions. The way you get out of dealing with fractions is you take the denominator of the fraction and multiply everything inside both equations by that denominator. So 2 times negative 2 is negative 4x, 2 times 4 is 8, 2 times 1/2 is 1, and 2 times 2 is 4. No more fractions. So we will subtract 1 from both sides on the x's and have negative 5x is equal to, let's also subtract 8 from both sides, which makes that go away. 4 plus negative 8 is negative 4. And that tells us that x is equal to negative 4 over negative 5, or 4 over 5. And then you're going to say, well, okay, that's nice. How am I supposed to find out what y is? You plug x back into your equations. So if I have x equals 4/5, I go back to 2x plus y equals 4. And I plug in 2 times 4/5 plus y equals 4. Do some arithmetic. Doing it on your calculator is not a problem at all. So you say 2 times 4 divided by 5, close parentheses, make it into a fraction, is 8/5. So I'm going to take and subtract 8/5 from both sides. 4 minus 8/5, and again make it into a fraction, is 12/5. Okay? So there's method number 1. If you prefer your graphing calculator, hit your y equals button, clear whatever's there, and enter the solve for y versions of the equation. So that's going to be negative 2x plus 4 for the first equation here. Enter. And the other one is going to be 1/2 x plus 2. And the way that I'm going to satisfy this is I'm going to go to the window and tell it to make the minimum x value 0. And I'm going to also go down here and tell it to make the minimum y value 0, because this tells me x has to be equal to or greater than 0. And y has to be equal to or greater than 0. So I can satisfy those two constraints by going to my window. So now I can just hit graph. And way down here in the corner, I see that I've got a little bounded region. So the only question is, which way did I shade, 0, 0 or not? Because if it's going to be 0, 0, it's going to be this little corner down in here. So 0 and 0 is equal to or less than 4. Yes. 0 plus 0 is equal to or less than 4. Yes. So my bounded region is that little region down in there. And I'm not going to draw this perfectly. I'm just going to sketch it. Let me come see what your error is.
Just gave me your, okay.
Mm-hmm. Okay, hit graph on the second. Oh, this, not subtract. I do that all the time.
Okay,
Now hit graph.
thank you.
And I don't always catch it either when I look at it on the screen. That's why I hit the go to see if maybe it'd give me a clue. Okay. So the thing that we just found was the value of this point right here. And if you want to find that, now that you've got it graphed on your calculator, it's easy to find. Second, trace, intersect. And it doesn't really matter where your cursor is. I'm just going to move it so I can see if I can. Okay, it's way out there. So yes, that's one of them. Yes, that's the other one. So basically, you just hit second, trace, number 5, enter, enter, enter. And it says there's your intersection point, and it gives it to you as decimals. If you really want it as fractions, and I don't care if you use decimals, that's fine with me. You say x, math, frac, and it'll give you x. And then alpha, y is on the number 1 key. Math, frac, and it'll tell you the fractional values, but I like the others just fine. They're just as good. So there's your intersection point. Okay? Now, the reason that's important is because our feasible region is, I now have all the corner points for it. Here's my feasible region. This is the point, I think, 2, 0, and this is the point 0, 2. If I want to know for sure, then I can find them two on the calc menu. So there's one of them. And there's the other one. And if I jump down to that graph, it gives me 0, 2. So those are my feasible. This is my feasible region, and these are my corner points. Okay? The only one I had to really work for was the intersection point. Now it says they want us to find, and this is the part where you're going to have to pay a little attention. It's not really straightforward. They want us to find the maximum value of the objective function, which is 3x plus 4y. And it has to be maximum according to one of the points that's in the feasible region, whatever gives us the maximum value for that. Now, the way that you find that, let's pop back over to the PowerPoint for a second. We just talked about the corner points. This is how you're going to maximize your objective function. The first thing you do is you choose the values 0, 5, 10, and 15 for z. Let me get a blank piece of paper here so we can actually work through this. So you'll understand why we're doing what we're doing.
How do you choose those values? Just
It'll be a little clearer when we get finished, but you just basically choose some values that are increasing in value, okay? And just choose something convenient. 0, 5, and 10, you'll know when you finally hit one that takes you outside the feasible region. So I'm going to do these one at a time. Let me write down the objective. Oh, I've got it there, so let me just go back over here. So here's our objective function. Z equals 3x plus 4y. Now, if I let z be equal to 0, I have 0 equals 3x plus 4y. I'm going to solve that for y. Which means 4y is equal to negative 3x. And if you want to put negative 3x plus 0 over there, that's fine. And that means then that y is equal to negative 3/4 x plus 0 divided by 4 is still 0. So that means that line is going to go through 0, 0. And it's going to have a slope of negative 3 over 4. Okay, there's that first line. Now here's what's going to happen. We're going to now choose z to be a bigger number, like 5. So nothing magic about 5, it's just that 5 is a bigger number and we want to move up. What we're wanting to do is we're wanting to move up the axis. So when we choose z is equal to 5, 3x plus 4y is equal to 5. Solve for y. y is equal to negative 3x plus 5. But again, when you divide through by 4, it's going to be negative 3/4 x plus 5. So this next line is going to have the same exact slope, except, 5/4, I'm sorry. It's going to have the same exact slope, except its y-intercept is going to move up. So instead of going through 0, 0, it's going to go through 0, 5/4, which is a little more than 1. Now, I'm not going to plot perfect points. I'm just going to try to keep my line parallel. So this is where z is equal to 5. Now, notice I'm still inside the feasible region, so I haven't maximized that yet. So I'm going to continue on, and I'm going to let z be a bigger number. Z is equal to 10. And if you followed the pattern here, you're going to realize quickly that it's always going to be negative 3/4 x. What's going to change is it's going to be 10 over 4 now, which is 2.5. So now the intercept is going to be, here's 2, here's 2.5. And again, the line's going to be parallel because it still has the same slope. I'm barely inside the feasible region. If I go to 15, that's why I said there's nothing magic about these numbers. And in fact, if you want it to come out nice and even, you can let it go to 16. It doesn't have to be incremented the same. (16 over 4 is 4. So let's see, here's 1, 2, 3, 4. It's going to go through that one. And again, I'm going to try to keep it as parallel as I can without actually drawing a bunch of points. Now, this one is completely outside the feasible region. I know that I have to be less than 16. Okay? It looks like I can be a little bit more than 5. I'm sorry, not 5. 0, 5. This one was 10. So this is the one that's barely inside. Okay? So that's why we chose those the way that we did. And I figured it was easier to show you sequentially than it was just to throw them up there and say, just do this. So what you're doing is picking sequentially larger and larger and larger values of z until you get outside the feasible region. Once you realize what's going on here, as z increases, those are called isoprofit lines. Even if you're not talking about a profit function, they're called isoprofit lines. And what you want to do with those is you use them to maximize. Y4, which is the last one we graphed, is not possible because all of its points lie completely outside the feasible region. The maximum possible value of z occurs between y2 and y3, which is somewhere between here and here. Now, we could have gone a little bit further outside, but the corner point of the feasible region that falls in the area between, and I think I have wrong numbers here, this should say between y3, and y'all correct this on yours if you've got the slides, and I'll upload the new ones. It's between y3 and y4, because here we're still inside the feasible region, here we're outside the feasible region. So the farthest point in between, still inside, and now we're outside, is point A. So point A is the maximum feasible value. Okay? Now, you don't always have to put in the isoprofit lines if you can start to realize if you let values of Z increase, where does Z go? Are you trying to maximize or are you trying to minimize? Okay? So if we were trying to minimize this problem, it'd be here. But if we're maximizing, it's going to go right here.
You're on your PowerPoint.
Oh, sorry. Thank you. So if we're trying to minimize, here's our minimum point at 0, 0, which, you know, duh, of course you're going to have 0 for whatever the objective function is if you don't have any of X and you don't have any Y. But since we wanted to maximize, that's kind of intuitively the maximum point. Okay? So all we need to do is find the maximum point and plug it into the objective function. It turns out that the maximum value for the objective function is 12. Okay?
Are you gonna upload this on there, because we don't have 3.2 PowerPoint on these books?
Okay, I will upload that for you. And you will get the corrected one. So I'm glad that I didn't upload it before. So we're going to go through and we're going to do pretty much the same thing, only this time we're going to do a problem where we're going to minimize a function. And this is probably going to be our last problem tonight because we've only got about 15 minutes left and everybody's wore out. So we have, this is the objective function. We want to minimize 2x plus 4y. And these are our constraints. And again, x being positive and y being 0 or positive are pretty common constraints in everyday life. And that's why we keep using those. So we really only have you're only going to have 2 other equations because you're only going to have 2 other variables. So when we graph the feasible region, it looks like this. This feasible region is unbounded. Okay, 0, 0 didn't work at either one of those constraints. So Z, again, if you let Z be 0, 10, 20, 40, 50, whatever, as you move further and further out, Z is going to be increasing in value. But our problem says that we want to minimize the value of Z, not maximize it. So our minimum value of Z is going to be all the values between 2.4 and 10, or 2,4 and 10,0 on this line, which is when Z is equal exactly to 20. And all of those XY points on that part of the line will cause Z to be 20. So any of the points on that line will minimize Z. So this is a place where you don't have just one solution. You have a line that gives you solutions. And that line is, where was my equation? Let me go back and get you the equation. So that you can actually see what the minimized part looks like. Was when Z was equal to 20.
Where did the 20 come from? I hate to be stupid.
No, you're not being stupid.
Again, we're just picking it.
No, this, remember we're going for a minimum value,
Yeah.
okay? This is outside the feasible region, so it can't be this one, can't be that one. That one is actually on the boundary of the feasible region, so it's possible. This one is all inside the feasible region, but the thing is, the values on this one are actually larger than the values here, and we're trying to minimize it. So we don't want to go further into the feasible region, we want to stay on the bottom of the feasible region. So that's why we picked the one where Z was equal to 20.
Okay, but there again, you just pick numbers.
Yeah, you just pick numbers, and in this particular case, it actually happened to land. What you probably want to pick is you want to pick numbers that are kind of in line with your corner points. because the corner points, I think you'll figure out really quickly, your corner points are going to be either your boundary or your feasible region. So when I chose 20, back over to the screen, because that one actually laid on the edge of the feasible region, then I have 20 equals 2x plus 4y. And if you want to solve it for y, you can, or you can leave it the way that it is. Let's see. Now, here's where the restrictions have to come in. They will suit this equation, which is the same as suiting that equation, so you can use either one, but you have to keep your x values within a certain boundary. So we go back to the graph. X has to be larger than 2. But less than 10. Any x values that solve that equation or that equation between 2 and 10 are solutions that will minimize the objective function. This might be a cost function. Okay? So you can refer to either that equation or that equation, but you have to add that restriction to it. Now, if you're given that you only have to have integer solutions, which in a realistic problem, you probably would only want to have whole number solutions, then you could actually figure out all of the max or the minimum solutions by choosing x is equal to 2, or 3, or 4, or 5, or 6, or 7, or 8, or 9, or 10. And then probably, I would use this one. It seems like it's easier to me. 2x plus 4y equals 20. So 2 times 2 plus 4y equals 20. 2 times 2 is 4. 20 minus 4 is 16. 16 divided by 4 will give me y is equal to 4. So there's one solution. And you could get all the others by substituting in x equals 3 and x equals 4 and so forth. Okay? But that's assuming that your only solutions would be integer solutions. I'm putting restrictions on it now that are not there. Because this is not necessarily an applications problem. So it could actually be any number whatsoever between 2 and 10 inclusive. Fractions, decimals, everything that's in that interval. Okay? Now, next time we'll actually do this process more in applications. But the thing I want you to leave with tonight is if you have a bounded feasible region, you can always have a maximum or a minimum of the objective function, because there's always going to be a highest value or a lowest value, one or the other. But if you have an unbounded region, you may not be able to have a maximum of the objective function, because that's going to keep on going out forever. But you will probably be able to have a minimum. I can't think of a realistic situation where you would ever be able not to have a minimum, because most of the time x and y both have to be positive. Okay, so realistically, you're not going to have to worry about being able to have a maximum but not a minimum. Okay? I will get this loaded up there for you. We have about 6 minutes left, and I don't think that's worth hanging out for. I am compiling the questions that people asked me over the last few days. The reason I was late tonight is because my brother is still in the hospital. He went in the hospital actually while I was in North Carolina at fall break, and he's been in there for a while, so I've been trying to run back and forth and check on him, and that's why I got stuck in traffic. So he's in pretty serious condition, so anything, you know, if y'all have any prayers to offer up, I would appreciate those.
That's your brother, did you say?
He is my brother, he is my only sibling. He's the last member of my immediate family. Yeah. And he's younger than I am, but he did not take care of himself, so.